Welcome back to this 7th lecture on this course on computational fluid dynamics. In this second part of lecture 7, we're going to examine how the Navier Stokes equations are discretized. We'll start off by introducing a problem that can occur if we discretize all the equations within Navier Stokes at the same point on our finite difference grid, point I, j. The presence of this problem means that we need to use a more complex discretization strategy, which we'll start to explain. What we'll do is we'll go through how we discretize the x direction of the Navier Stokes equations in some detail. A similar approach is used for both the y direction and, if applicable, the z direction, and so understanding how it's done for the x direction assists us in building the bigger picture. When we do this, we're going to illustrate the method of using central differencing for every term in the equation because it keeps the explanation simpler. However, we need to be careful because we already know that convective terms in transport equations need more careful treatment to take into account the direction of information flow in the problem. Hence, we would be using for these terms a more complex discretization algorithm in reality. I'll remind you that we've made this simplification for the purposes of a clear explanation at the appropriate place in this part of this lecture. By the end of this part of this lecture, we'll be in a position to see how we build an algorithm to solve this set of discrete equations, and of course that is going to be the subject of the final part of this lecture. Now, let's introduce a problem. Here on the whiteboard, I've put a statement of continuity. d by dx of my x direction velocity u plus d by dy of my y direction velocity v equals 0. As we'll see in the final part of this lecture, when we solve the continuity equation, we're not actually going to be using u and v as we understand it, but we'll see that complication later on. Let's for the time being say that we're going to solve this and assume that continuity always holds. So du by dx plus dv by dy has to equal 0. Now on the board I'm putting a grid of finite difference nodes. This is the two-dimensional grid of nodes that we've seen before when we solved a transport equation in 2 dimensions, and I'm using the ij notation here rather than that single index k. And I want to focus on point ij in this grid, which is sort of down at the bottom right, and now I'm going to superimpose on this grid arbitrary values of my x direction velocity u and my y direction velocity v. I've put the u values in green and the v values in purple. And what I want to do is illustrate how nonsensical this is, but how mathematically correct it is. Let's take our continuity equation at point ij and see what it evaluates to using this velocity field. So at ij, if we look at the x direction, which is there in green, and if we take central differences at point ij, we've got -5 minus -5, which equals 0. Fine, okay, so it's over 2 delta x, but we've already got 0. Let's take the y direction. So in purple we've got central differencing 20 minus 20, which again equals 0, despite the fact we're divided by 2 delta y, but it's 0 anyway. And so continuity using this velocity field is obeyed. Now let's just look at this velocity field in a little bit more detail. If we look in the x direction at those green values, and if we go from left to right along a given row of nodes, we have, say on the top row, 2 minus 5, 2 minus 5, an alternating pattern which will repeat ad infinitum in the x direction. In the y direction, let's again look down, let's say the far right hand column. We've got 20.5, 20.5. Again, it's an alternating pattern. So this alternating pattern will give us the correct result for evaluating the continuity equation. But it's absolutely non-physical. You're never going to have an alternating pattern of velocities like this in nature. And so what this illustrates is that if we use the same ij point to evaluate my velocity gradients in the x direction and the velocity gradients in the y direction, we can unwittingly end up with a solution that's absolutely nonsensical. So with this short illustration, what it motivates is the use of a different kind of grid to solve the problem. And what we actually end up using is something called a staggered finite difference grid. So let me illustrate what I mean by a staggered finite difference grid. So here on the board I'm going to put down a diagram which is my two-dimensional array of nodes again, and I'm going to use the same ij indexing notation that we used on the previous slide. And what I'm going to do is say that at every ij point, I, j plus 1, I minus 1, j minus 1, wherever those intersection points happen, I'm going to evaluate pressure. Now, as we'll see later on, we actually evaluate pressure using the continuity equation, but we'll deal with that subtlety later. But at each whole number, I, j, I plus 1, j, and so on and so forth, we evaluate pressure. Now, let's think of x direction velocity, which is u, which I'm now colouring red. I'm going to evaluate my x direction variables at halfway points in the x direction. So at I plus a half, j, I plus 3 halves, j, I minus 3 halves, j. Finally, in my y direction, I'm going to evaluate my y direction velocity, v, which is here in purple on the board, at intermediate points in the y direction. So it's going to be I, j plus a half, I, j plus 3 halves, I, j minus a half, for example. And so what we end up with is each of the equations that we're solving discretized at a subtly different point on our grid, and this is the way that we avoid this problem of checkerboarding. Now, what I'm going to do is to go through in some depth how we discretize the x direction of the Navier Stokes equations. We're going to be using that point I plus a half, j, and what we're going to do to start with is to look at how we deal with the pressure terms. Now, if we think of pressure, we said that pressure was evaluated at each intersection point on this grid that I've drawn, and so I've highlighted on that sketch of my array of nodes in light blue each of those intersection points. There's 2 nodes that are uncoloured, but we'll see why they're uncoloured in a minute. So that's where my pressure nodes exist, but in the x direction for the Navier Stokes equations, what I'm going to do is discretize everything at point I plus a half, j. So pressure in this case would be discretized here. Now, I've got a symbolic notation convention here. Square symbols means that that parameter in question doesn't exist at the point I've drawn it. And we know that pressure only exists at intersection points, which are the round circles. So there's a square symbol there in blue because there isn't a pressure node there. Filled symbols means that the data exists. And so what we have is dp by dx discretized at point I plus a half, j. I'm going to use centre differencing because I know that at point I plus a half, j, I've got a pressure node half a node away from me at I plus 1, j, and half a node away from me in the other direction at I, j. And so it's going to be pi plus 1, j minus pij over 2 delta x. Well, delta x is the spacing between half nodal points. Okay, so let's turn our direction to x direction velocities. And let's have a look at the first term that involves x direction velocities spatially, which is d by dx of u squared. So this results, of course, from our convection term, and that u squared came out of the conservation form of the total derivative that we looked at earlier. Now, big disclaimer here, of course, this is convective. You shouldn't be using centre differencing here because we know that information flow is important, and so what we should be using is one of these multi-point upwind difference schemes such as SPUD or QUIC. However, that will not assist the clarity of this explanation, and so I'm going to be using centre differencing for illustrative purposes only. Please remember that. So with that caveat over, d by dx of u squared, I'm going to evaluate again at point I plus a half, j. Now, if we look at my sketch on the board, we've got a different set of nodes now coloured. Now, those nodes I've highlighted in pink are where my x direction velocity variables exist. The ones I've highlighted in red are the ones I'm actually going to be using in the difference calculation. And so we're calculating at point I plus a half, j, and we're going to be using information from I minus a half, j and I plus 3 halves, j, and using a centre difference there. Okay, so there we have how we would discretize d by dx of u squared. So let's hunt for other u direction terms. We've got another u direction term in the right hand side of this equation, so it's d2u by dx squared. And again here in brown I've written what that statement is, and I've coloured in brown the nodes that I'm using, and I've still got those pink nodes there because I'm still dealing with the x direction velocity, which is of course u. And so I've got a second order derivative, and so I know how to write centre differencing for a second order derivative, and so I'm going to be using nodes I plus 3/2 comma j, I plus 1/2 comma j, and I minus 1/2 comma j. And this would be a valid discretisation to use because the d2u by dx squared term is not convective, and so centre differencing here would actually be correct. Okay, let's have a look at something a little more complicated. On the left hand side of this equation again, we've got another term that drops out of the convective bit. So again, using that conservation rewriting, we've got d by dy of the product of u times v. Now we need to be a bit more careful here because we've got both x direction velocity and y direction velocity involved. Since this is still the x direction Navier Stokes equation, we are still discretising at point I plus 1/2 comma j. So here in green I've written the derivative down, it's at the bottom of this list, and so I'm going to have to interpolate one of the directions, because if we think of the y direction, we know the y direction variables are stored at I comma j plus 1/2, I comma j plus 3/2, and so there's no y direction information at half node spacings in the x direction. So where I've drawn that open green circle, which is above the open green square, then that open green circle represents an interpolation of my y direction velocity from its two nearest neighbour nodes, which I've shown in pink. And likewise, that open circle below the open square is again an interpolation of the y direction velocity from its nearest neighbour nodes in pink. So from those two interpolated y velocities, I can then use a derivative in the y direction, a centre difference again, to get an approximation to what dv by dy is. But of course we're not calculating dv by dy, we're calculating d of uv by dy. And so what we'll also need to think about is how we interpolate x direction velocity data onto those points as well. Now we know that x direction velocity data exists at I plus 1/2 comma j, I plus 3/2 comma j, and so on and so forth. It doesn't exist at the j plus 1/2 and j minus 1/2 point. And so those nodes in light red on the nodal diagram there show where the x direction velocity data is held, and again we're going to have to interpolate that x direction velocity data onto the location of our open green circles. So the d by dy of uv term is a bit more complicated to calculate because we need to interpolate both x and y direction velocities onto the I plus 1/2, j plus 1/2 positions in order to be able to take that centre difference in the first place. And of course the additional complication, and that same caveat again, is d by dy of uv drops out of the convection term, and so we know we shouldn't be taking a centre difference here because we need to take information flow into account. And so the actual nodal pattern that we'd use would be that according to one of the multi-point upwind difference schemes such as Spuds or Quick, which would make this illustration really quite messy, which is why I'm illustrating using centre differencing. Okay, so that's d by dy of uv. The final term we'll look at is another y direction derivative, but of my x direction velocity, so d2u by dy squared, which is the final term on the right hand side of this equation. Now this is quite nice because if we're evaluating this at point I plus 1/2 comma j, then of course we've got all our x direction velocity data at I plus 1/2, I minus 1/2, and so we can just take a centre differencing using the nodes here in purple, and of course it's a second derivative, and so we'll be using I plus 1/2 j plus 1, I plus 1/2 comma j, and I plus 1/2 comma j minus 1 as all the nodes that we use in the evaluation of that gradient. Okay, so what we have, to summarise, is the x direction Navier Stokes equation that I've just put up here with those four different colours of terms, and we're evaluating all the gradients for this x direction Navier Stokes equations at point I plus a half comma j, which is represented by the square in this pattern. And what I end up with is something that I call a stencil. This pattern of nodes here that I've coloured in respect to each of the terms it evaluates is giving us graphical information as to how we're discretising those equations. And so the stencil that we have here is a stencil that is all down to using centre differencing. We can imagine that the shape of that stencil would change if we'd actually and correctly used, say, the quick method to discretise those terms that are dominated by convection, the red terms and the green terms. Apologies for those of you who are colourblind. So, what we're going to do is to now take this methodology and we're going to use the same idea for the y direction of the Navier Stokes equation. So, before we do that, we need to consider how we discretise in time. We've discretised in space. We've done our spatial discretisation. Let's consider the time derivatives. So here on the board again is my x direction Navier Stokes equations. I'm going to rearrange this such that partial du by partial dt is the subject of the equation. And then I'm going to call all those terms on the right hand side of this equation shadow A. So if I want a time step, I know the simplest way of doing it, using first order time derivatives, is that saying that u t plus delta t is going to be u of t plus a times delta t. So the x direction velocity at my next time step is going to be my x direction velocity at this time step plus all the terms that lead to that change in x direction velocity, which are the terms on the right hand side of this equation. Of course, again, this is a simplified illustrative way of writing that time step. In reality, you're probably using a fourth order Runge-Kutta approach rather than a simple first order differencing. And also for that a delta t term, it's highly unlikely you'd be adding all of a delta t to this equation. You'd probably be putting a relaxation factor in here, so you're only adding a fractional amount of the change at each time step, such that you don't end up with forcing your solver into some kind of instability. So there's a lot of extra complication that actually goes into this, but hopefully this is clear enough and simple enough to get the picture of what's actually going on. Now let's turn our attention to the y direction Navier Stokes equations. We're going to discretise at one of our y points, and our y points is at our halfway positions in the y direction, so for example I comma j plus a half. We'll take our y direction Navier Stokes equations and we will take our grid. There's my finite difference grid again. I've put a large cross through where we discretise the x direction. Now I'm going to highlight where we're going to discretise the y direction. And so we can see where that square is, that red square with a blue border. That is the node that we're going to use to discretise the y direction of the Navier Stokes equations. So I'm not going to go blow by blow through all of this before. It's essentially the same approach that we took in the x direction. We're going to have to use some interpolation nodes for our x direction velocities, and we're going to end up an equation for my y direction velocity, which is v, that we need to solve in time, and it's going to have a form very similar to its x direction counterpart. So v at t plus delta t is going to be v of t plus shadow b times delta t, and shadow b here is all those terms that are spatial in origin rather than temporal, because if you remember, what we did was rearrange this equation such that now dv by dt would be the subject, and everything that dv by dt is equal to would be shadow b. And again, this is illustrative. This would be solved ordinarily using a fourth or fifth order Runge-Kutta, and we'd probably have a relaxation factor pre-multiplying that b delta t term. So the final equation that we need to solve is continuity. And as we will see in the final part of this lecture, continuity actually helps us solve the pressure field. We'll worry about that later, but because continuity helps us solve the pressure field, we're going to discretise continuity at our pressure nodes, at our I, J nodes. So this actually seems quite simple. There on the board at I, J, I've put a big red square with a blue border. And if we think of du by dx, those we're going to use centre differencing with the red nodes left and right of that red square. And dv by dy, we're going to again use centre differencing with the nodes top and bottom of that red square. And again, centre differencing here would be a valid approach. Now, there's some subtleties that we'll talk about in the final part of this lecture, but we'll see that we're not actually solving continuity directly. We're going to assume it's true and just take it as a fact. We're also going to see that the x direction velocity and y direction velocity that we use are obtained from sort of versions of equation A and B that we've just seen on the previous slides. So we're going to be calling this continuity, and let's say that this is equation C. So we've got equation A, which is our time stepping for the x direction Navier Stokes equation. We've got equation B, which is our time stepping for the y direction Navier Stokes equation. We've got equation C, which is continuity. Now, equations A, B and C are all going to be talked about in some depth in the final part of this lecture. So let's summarise with a few key points. We started by introducing a problem, and that problem was that you can end up with a nonsensical flow field that is mathematically correct if you evaluate your x and y direction Navier Stokes equations and continuity all at the same I, j node. And this motivated us to use staggered grids. So all x direction Navier Stokes equations get discretized at points that are similar to I plus a half, j, a halfway node in the x direction. All y direction Navier Stokes equations get discretized at a node that is halfway in the y direction, for example, I, j plus a half. Continuity, which ends up being intimately involved in pressure correction and pressure calculation, gets discretized at point I, j. Just a reminder of the caveat, in all through this lecture we use centre differencing for means of a clear explanation, but please don't forget the fact that convective terms would need higher order upwind differencing, and we also used first order time differencing again for clarity of explanation, but in reality don't forget that you'd be using fourth or fifth order Runge-Kutta based approaches.